Yeah. Yeah, I think we kind of.
All right, good afternoon, everyone. Day three here, panel three of day three. Thank you so much for joining us. My name is James Okulums, Director of System Planning at ESIG, and I am feeling very fortunate to be introducing this next panel. This is a topic that is near to my heart on advanced grid technologies. And we're going to have a wonderful session here talking about frameworks within organizations. How do you actually think about ATTs and how do you take it for something that's conceptual, looking at just taking a compliance check mark to operationalizing it, right? How do you actually go through that process? And so we'll have a wide range of perspectives here this afternoon, and I'm really excited for it. I'm excited for you to join that conversation. So I'll pass it over to Madeliene, who'll be chairing the session. Looking forward to it. Thank you.
Thank you, James. That pretty much covered what I was planning to say as an introduction. But we're going to start off with Zach talking through the regulatory landscape and sort of some of the external pressures that organizations are having to develop these sorts of frameworks to integrate the tools. And then after that, we'll go one by one through Alberto and then Matt and then Raj speaking about the specific frameworks, how they've been developed at their different organizations, and how they've been actually used and implemented within utilities. So with that, I'll send it to Zach.
Okay. Hi, everyone. My name is Zach Zimmerman. I'm a Director of Research and Policy at Strategies. Apologies that I'm first up after lunch here. I will try to not put you all to sleep here with my presentation. Wanted to start off today talking about some of the work that we do at Grid Strategies. We started two trade coalitions, the WATT Coalition and AMP Coalition, which are trade associations for both grid enhancing technologies and high performance conductors. And so some of the slides I'm going to run through today are related to the work that I do with those coalitions and the vendors of some of these technologies. So for the WATT and AMP Coalition, we often talk about these technologies under the framework of advanced transmission technologies. So these are technologies that can cost effectively increase capacity, efficiency, reliability, and safety of power lines faster than traditional upgrades and at a lower cost with higher net benefits usually. The technologies we cover, the ones that are within our coalitions, there are obviously other technologies that we think fall inside this advanced transmission technology umbrella. But for the WATT Coalition, there's kind of three technologies that are focused on, and these technologies are ones that kind of dynamically alter the grid capacity of the grid in some way. So these are dynamic line ratings, advanced power flow control, and topology optimization. So these are hardware, software. Dynamic line rating uses real-time weather and ambient data to adjust line ratings. Advanced power flow control kind of pushes or pulls power to redirect it onto underutilized circuits or direct power off circuits that are overutilized. And then topology optimization we kind of talk about as the ways of the grid, which is just looking at grid reconfigurations in an automated process. And then on the AMP Coalition side, we're focusing primarily on new types of conductors. So one category is carbon core conductors. So these replace the traditional steel core of a conductor with some sort of carbon fiber or composite core, which is lighter than steel, and so provides some capacity and efficiency gains compared to more traditional conductors. And then superconductors obviously use specific metal alloys that are super cooled and allow for power to be transferred with almost no losses. So those are the technologies. Just wanted to cover a few major deployments. I think how we would frame this for both of our coalitions is that we've continued to see a steady march forward of different deployments and adoptions by utilities and RTOs around the country. So you can see here, Entergy in Texas, Louisiana, and Arkansas had the first multi-state deployment of DLR line ratings. This was a pilot, though. Ameren also announced the pilot with DLR where they were deploying sensors on some of their most congested lines to get better real-time data. And then in PG&E and Georgia Power, they have both are in the process of or have recently deployed advanced power flow controllers to unlock, in both cases, around 100 megawatts of new capacity to address load growth in both of their regions, both of their footprints, and are expecting, and in Georgia Power's cases, are expecting to continue with the deployment. And then for topology optimization, we've seen various iterations of grid reconfigurations being approved in MISO, ERCOT, and SPP. On the high performance conductor and reconductoring with high performance conductors, KISO, I think, is one of the leading RTOs or ISOs when it comes to integrating some of those deployments within the ISO. So I'm going to cover a little bit of the regulatory landscape and where things stand and why I think we see this kind of steady march forward. Since over the last about 3 years, there's been 19 states that have passed legislation related to advanced transmission technologies. So we have kind of identified 3 key themes that have driven this interest by states and the passage of these laws. And these laws have come kind of on a bipartisan basis across the country. So the 3 main things are load growth. There's a lot of states are facing a significant amount of load growth. And then alongside that, there are concerns about rising electricity prices. And so load growth and affordability, that kind of combination is leading to this increased interest from states around some of these technologies that may be able to be deployed faster and unlock capacity at potentially a lower cost than a traditional upgrade. And then at the federal level, we're also seeing kind of a series of orders that have also, I think, driven more adoption of these technologies. So that would be FERC order number 881, which with 20 were interconnection and long-term transmission planning rulemakings that required the consideration of subsets of advanced transmission technologies within them. So all of these rules are essentially making utilities and RTOs and ISOs really look at their planning processes and try to figure out how to take these technologies from maybe the pilot stage into further kind of integration within their systems. The other thing I wanted to deep dive into is we've seen legislation emerge in much more than the 20 states or 19 states where laws were passed. That legislation kind of falls into 3 main categories. We see study requirements, reporting requirements, and laws that we kind of broadly categorize as trying to motivate deployment. So within the study requirements, on specific studies that are looking at beneficial deployments as well as just mitigating congestion. Sometimes you also see studies that are just like a landscape study of what's happening across the country. Reporting requirements tend to be require utilities to consider advanced transmission technologies as an alternative in CPCN or siting and permitting cases, or they may require utilities to report on how they are planning with advanced transmission technologies within their IRP process. And then lastly, motivating deployments. Some laws have passed some versions of incentives or allowance for cost recovery when deploying these technologies. Though to the best of our knowledge, I don't think any of those incentives have been used at the state level. Passed study legislation in 2024. Their studies kind of happened in 2025 with early results in 2026. So just wanted to give you all a flavor of kind of how utilities are taking the legislative text and turning it into an actual study, and then how PUCs are kind of and ISO RTOs are kind of responding to what is being produced for them. For California, this is like the first of a reoccurring study. So the GETS portion of their study is every 2 years, and the reconductory studies every 4 years. Whereas Minnesota, at least for now, was a one-time study, but may transition into a more into a reoccurring study. So quick overview of the language. The California bill takes kind of a broader approach. It just more generally says that utilities should study and identify projects, GETs or reconductoring projects that can achieve one or more of the following benefits. So you see the benefits there. And then to essentially develop an implementation plan related to those. So there are three main IOUs in California that had to respond to this, and they did so in various manners, I would say. And so just wanted to get into some details of that. So the three IOUs are San Diego Gas and Electric, Pacific Gas and Electric, and Southern California Edison. And essentially what they did, we can potentially get into some of the details of these studies in the question and answer portion of this, but the three utilities each submitted separate plans and each kind of used different methodology within those plans. They used a combination of reliability plant power flow cases that had already been developed by CAISO in previous years, or the existing 2025, 2026 cases. They also, in some cases, use the economic assessment, which was production cost modeling, to look at congestion and curtailment data in some cases. And then in other cases, they kind of just did a systematic evaluation of their systems. So what we saw out of that is, there's a lot of differences that arose within those studies. The utilities didn't necessarily have a standard approach. They also each kind of looked at different project level screening criteria. So in some cases, this was simply just considering advanced transmission technologies as alternatives, but some of the utilities did go a little bit further and tried to develop specific project level screening criteria as a part of the study. So you can see here, just as like some basic examples, that APFC or transmission topology optimization were excluded when the lines they were looking at were radio lines that weren't meshed with the rest of the system. That is a good screening criteria because it doesn't allow for power to be redistributed. As an example, for high performance conductors, these conductors can typically increase capacity by up to maybe 75 or 100%. And so any circuits where there was thermal overloads between 20 and 100%, those were some of the screenings that were being developed. While I do think there's a lot of like good progress here, I will say that, and we'll get into some of the like limits to the scope of this evaluation. So what do we learn from the results? For Southern California Edison, PG&E, and SDG&E, there were no transmission topology optimization or advanced power flow control opportunities that were identified. So I think so that's one piece of this. For dynamic line rating and high performance conductors, there were actually quite a few opportunities that were identified. There were 23 DLR lines that were identified for CAISO to do further evaluation on, and 62, I believe, potential high performance conductor candidates that were essentially screened as good candidates for if future reliability or economic congestion issues arose. So those are kind of the results. There's no real implementation that came out of this. There were projects that were proposed for CAISO to look to study further. And unfortunately, no benefits were quantified for these projects. So despite identifying that these projects might solve like a reliability or economic need, the specific benefits were not evaluated for these projects. So in terms of lessons learned, that was one of the ones, is to make sure to consider net benefits when you're looking, when you're evaluating these projects. We also think that a whole of system analysis would be better. For in some of the cases, utilities just looked at 10 previous reliability projects that had already been identified in CAISO studies and did an alternatives analysis. We don't think that that's really the best way to identify some of the broader network effects that you can get from advanced power flow control or topology optimization. And then the other thing to note is that there was a mix of reliability and economic cases that were used, and ideally there would be a better integration of those two, where both economic and reliability needs are considered together. Transitioning to Minnesota, the interesting difference between Minnesota and California. California's study requirements were much more open-ended, essentially asking the utilities to identify beneficial projects. Minnesota was much more narrowly tailored. It focused on relieving congestion on transmission systems where there was locations that experienced 168 hours of congestion, or the 10 most costly areas of congestion. They looked at both historic and also forward-looking congestion. And so based on those identified congestion needs, either from historic data or forward-looking data, then the utilities essentially did a implementation plan where they tried to evaluate whether DLR, advanced power flow control, or topology optimization could resolve any of this congestion within a 5-year payback period, which was set by the commission. So the interesting part of that, I think, again, is this more narrow scope. It didn't have the broad range of benefits that California did, but it solved a much more specific need, and then developed a plan that had a payback period tied to that specific congestion need. So within the study, they used the day-ahead congestion reports, identified 66 constraints. Of those constraints, 12 were identified where a DLR solution might meet the required payback period, and then they included an implementation plan. The Minnesota PUC is still evaluating these reports and is expected to, I guess, rule on them as to whether the utilities should move forward with them. Oh, the computer might be shutting down here. Oh, no, we're back. Okay.
I need an advanced technology.
Yeah. No, we're oh, but the slides are not advancing now. There's no message. The screen just went blank.
Put this on the list of advanced technology tools to develop.
While we're waiting, I grew up hearing the term facts. Do that anymore. Do you not use that term anymore?
No, facts are still devices that are used by utilities. Advanced power flow control are like a modular kind of redeployable version of facts. So facts should still be something that utilities evaluate and deploy, but there's advanced power flow control is kind of like the next iteration of that.
Yeah, when I talk about like the ability to control the power of AC, should I be using advanced? Like, could I be using that term to communicate this general concept?
Well, I mean, if you ask me, I would say they're separate devices, but I think it probably depends on who you talk to as to what they would say. But I would say that they're separate devices, or like they're both power flow controllers, but they have separate like benefits and capabilities.
It's the generic term we should be using to describe things that let you control power on an AC network.
I would just say power flow controllers. I don't know if anyone else has other thoughts.
The facts concept started in early in the 90s.
Use your mic.
So the fact devices started early in the 90s, and then they developed two for sound devices and series devices to control power flow. In fact, the SSC that smart wires that adapted is based on that initial design. And then over time, the more sophisticated ones like a UPFC, they were abandoned. And most of the facts nowadays are STATCOM or SBC. So people call them facts when they refer to STATCOM or SBC, essentially. I didn't answer your question which one to use, but so I guess I tried to explain why.
I can use this mic. Okay, I will just finish up at this last slide and then we can move on to other speakers. So I think what we're working on developing for the 1 amp coalition is kind of our own internal framework of like, what does it mean to study advanced transmission technologies more holistically? And so this is kind of what we've started to put together as a framework. So start with your goals. Obviously, we've seen through different legislative efforts that can look very different. We do think that defining those goals ahead of time and can be very helpful. So even if it is just like a narrow frame of addressing congestion, that can be a good starting point for utilities to kind of work on studying these technologies and getting up to speed. We also think that addressing both reliability and economic constraints within the same study process is important. So that might, for example, just start with some economic screens related to congestion or curtailment, then going into reliability considerations, and then on the back end, after solutions have been developed, make sure to quantify the benefits. So the other piece of that, when we're identifying reliability and economic needs, we think that there's we recommend using a loading order approach, which I think in our minds essentially is the idea of deploying the like lowest cost, fastest deployed technologies first, and then doing that in an iterative process. We do think that there's a need for some kind of like heuristics or rules of thumb to be developed for planners to, when they see specific needs, they can automatically rule out some technologies or potentially know that this is a good candidate for those technologies. And then lastly, I think there's just more work that needs to be done on quantifying benefits. So the Minnesota study is good because it focuses specifically on congestion. That's like a narrow benefit that you can measure and quantify. But I think long term, we want to move to considering some broader like production costs, benefits, avoided or deferred transmission projects that may be that you could get savings from with a deployment of advanced transmission technology. So right now, none of the studies that we've looked at have actually kind of systematically quantified those benefits. They've kind of done like the least upfront cost, and they've done like the engineering screen of does this meet the need, and then kind of looked at it on a I'll leave it there for whoever's next. Thank you.
And I'll just say, well, you can please note your questions down for all the presenters, and at the very end, we'll invite folks to ask your questions.
Right. Hello, good afternoon. My name is Alberto del Rosso. I'm with EPRI, area manager in the transmission operation and planning group. I want to talk. Can you hear me well? It's coming on. Yeah. I'm going to talk about some work we're doing more specifically on what we call the framework to evaluate GETs. The need for methods and criteria to evaluate them. We've been working on this here for a long time, way before the GETs terminology was coined. But starting like 2-3 years ago, we realized that there was a need to really move this forward, not just the piecemeal research that we were doing for a long time, try to accelerate this because the industry needs something fast. So to start from a little bit from the beginning, GETs and where's the role of GETs in the transmissions apart from the legislation requirements. So we think that it can play a role in different ways, and it can be a bridge between the needs now and the long to be the backbone of the transmission system, right? So there's no way around that. But the technology can play a role on help and getting to that at that point, either as a temporary TRL, fully commercial TRL, and there's still some challenge in terms of implementation. If you think that the one on the middle, when we talk about the needs and why with 25, what are the barriers for large adoption? If there's one aspect that needs to do with how to understand and how to use them. So we work on those 5 domains that you can see there. Technology evaluation. So we need to understand what technologies can do and what they cannot do. Integration into planning system, that's precisely the topic of this conversation now. Integration to operation. If you're going to put devices there, you need to model them into the MS. You have to have a specific procedure to operate them and normal then contingency conditions. Technology acquisition and maintenance is not just buying the technology now, but how long it's going to last, right? Where's the maintenance plan? If I put a power electronic there, do I need to do an overhaul? Then 10 years, 15 years, what is the cost of that? How to bring that cost into my solution or decision at this point? And then the topic that always is up there in terms of the incentives and market, which not we're not dealing with this in this conversation, but that's one of the aspects as well. So in the end, what we try to do with this, all this framework, and is, as I said in that part there, GET should be treated as first-class option on every transmission plan and not as a pilot, not as an exception. That's the goal at the end. We focus on these 4 technologies, and we can argue that advanced conductors or some cases, like he mentioned, there's some separators has the technologies. We focus on that when we talk about advanced conductors, and this within this context is reconductoring. In many cases, you can reconductor and can keep some structures. So we say we're getting more out of the existing, the concept of getting more out of the existing infrastructure is still there. What is and what is not the framework that we're doing? We try to provide, develop methodologies, tools, handy tools, and information for planners to feel comfortable doing the analysis on these technologies. It's intended to leverage the existing process, not to say, okay, forget about everything you're doing planning, do this. No, it's just incremental upgrade on things that everybody's doing and accommodate different needs as well in terms of the time frame for the planning and the scope on spatial scope and so on. What is not there, and this doesn't have to be strict, let's put it there, but it's not a process. You say it's recipe, you follow this step by step. It's not intended to replace the existing planning processes. It's not in our intention to impose principle of a standard around this. Okay, it needs to be this way. So it's more the how doing things rather than say need to do this and very specifically. With that in mind, so say how we can help in doing this. So think about a process when we want to evaluate and select the best option considering GET. There's a full product and doesn't have to be necessarily that linear, but it takes the main steps that you do, right? Start with identification of your needs or the bottlenecks in the transmission network. Then you need to see how you need to map potential solutions to those specific needs. All those 4 technologies we're dealing with, we group them under grid enhancing technologies. They're very different, right? What you can get of a advanced conductor is very different on DLR or even topology optimization. And they need to evaluate then, they need to understand the economic benefits of that. So you have to have good processes to do that. And you need to characterize the reliability once you select, okay, this is make economic sense. Now, where's the risk that I run into that? When there was an early conversation this morning on the second session, there was the common risk came out many times. Okay, we need to understand what we run into, right? And then at the end, well, the project selection and do we really have all the criteria to make sure that we're exploring the capabilities of these technologies? The description on the green blocks are the things that we're developing and within this framework. If you think about how do we map? And first have to understand what these technologies can do. There are some salient characteristics that they have, which can differ from the traditional solutions. So I listed few of them, and then we need to understand, again, they are different from each other, and it's qualitatively at least understand what is good for transit, what is not. So we have a capital cost, right? Very critical in the determination. The lead time also, because sometimes we say that enhanced technologies can help providing the solution in a timely manner. Sometimes the best solution is probably build a line or expand the network, but it's not coming on time. So they can help this and buy some time. The outage required maybe it could be minor because it also can be important aspects. We were discussing with some entities say, well, we cannot take the line out to put a new conductor. So we need to find something that it help quickly. The last, I would say, portability and reversibility. And this concept actually came up mostly on the advanced power flow controllers when they build the modules that can be relocated in different, and that's open another opportunity because you can have interim solution and then use part of that, not all, but part of that, and when without needs or needs in other places. So that adds another extra benefit that was normally not considered in the planning process. The free transmission capacity, of course, is very, very important, right? It's we're going to put there, they're going to give me really the capacity that I need. Clearly, with a conductor, that happened. A DLR is just a statistical value here, so I need to understand how much you can get out of that. And then when you understand those capabilities, you can map with the different needs. And I put a few of the needs there. Reliability-driven projects, probably the most common one. So you run a long-term planning, identify bottlenecks, and then you need to define what technology to use. The congestion is more economic aspect, right? You resolve congestion if there's economic benefit out of that. If not, you don't do it. And like the reliability. There are specific aspects or problems like a loop control or contractual path that's interested in using phase shift transformer for a long time for that. So there's a very neat implementation, but also it's one of these technologies can help with that. And you can think about other problems that they need to solve as well. So how they map. And then that's the first step, and then comes to say, okay, we need a specific process for each of them. I'm going to explain a little bit more on this. So, well, we have been developing that. Again, keep in mind, as mentioned before, the framework is about to help how and provide some practical tools to do the analysis. Well, there's requirements from the two for order, right? Some of the requirements from the states consider DLR as a solution for long term. DLR, as I said, is not giving you a firm capacity. It depends on the weather. So how much can I get, and how can I characterize that, and what are the risks if I consider that I'm going to have in that line maybe 15-20% more capacity, and what's the level of confidence and the risk associated with that. So all that analysis needs to be done. That's the process that we have developed for that. Also, as a handy tool, we realized that it's not that easy to get and obtain DLR data. I want to evaluate several lines, right, in the planning process. So we created that tool that read weather information and create a synthetic profile. It's not, we tested that with the real DLR system, and it works okay for the process, for the purpose of this type of analysis. In advanced power flow solution, again, this is something that I mentioned been working for a long time. We developed this software tool because it's very difficult when you have to solve many problems at the time, many scenarios, do one by one just by visual inspection. You may find a solution that works for one, but it may not work for the other, and so on. So, and we're not saying that need to use that tool. This is one, many of the others, and there are some other methodologies that can be implemented for that. That's, again, that's another thing that we are providing along with this work. When in reconductoring, we work this with our expert in the transmission station area, and they're expert in designing transmission lines. We talk to them, okay, can we reconductor this line? The first thing is, okay, give me the information about the towers, give me the terrain, give me. I say, no, wait a minute, we're doing planning. The only thing I have is a powerful model, and eventually I can give some a bit more. So we need to have a way to estimate the possibility of doing that and come up with some parameters that I can put in the planning and compare the solution against others. If that's merit better or is better, then you can go to the next step and do a more detailed evaluation. So all that part is also being developed here. Well, actually it's developed already. And this is one probably is a bit more, say, controversial point. And the order required to look at transmission switching. They don't call it transmission optimization, but it's essentially the same. The key question is, can I use, can I defer the construction of a new transmission line or substation because I identified there can be some switching actions that you can take in the network, either open, close the line, but it's more important is splitting substations. Well, that's sort of uncharted territory. We're starting, we haven't seen any analysis of that. The first reaction of planner says, no way, right? No, I'm not going to rely on that. I need to build, because when you do planning, you build margin, you build capacity to deal with situations that you expect happen, but many other millions of different conditions that you cannot expect when you do planning. So by doing this, you can identify opportunities, but you need to be careful because you're not building that margin. So our analysis we're doing with several members to trying to understand. The only way to really understand is to run cases, and many cases, and yes, a bottom-up approach, understand what are the risks and benefits. The risk assessment, so I mentioned that in that blog, the 4 blog on that process. There are, when we do planning, we normally define really understand all the risk that can be specifically out of these technologies. For example, if you put 2 power flow control devices that are going to be, they need to be operated in a centralized manner. It could be a PLC, it could be an EMS with a dedicated communication system with a control scheme that can fail. So you need to understand that there's a failure mode to add to the analysis. If we talk about DLR for plan, I mentioned before, there's a statistical value that you can get of that. So I need to understand that how they work and evaluate the risk properly. So we're working on that. Again, there are specific things at risk that needs to be considered for each of the technologies. And then we have all of that. And there are the cost, of course, is an important one. There are other aspects, and because there are known technologies that you do all the time, they know there's a sense of which one is it really solve the problem. And when it comes to this, there are other benefits that you can get out of them, like for example, the ability to move from one place to the other. The ability that gives you the possibility to do solve interim solutions, but also adaptive solution, right? One of the key aspect of transmission, non-transmission plan is uncertainty in the future conditions. And if I build, assuming certain future scenario, and that doesn't happen, I ended up with stranded assets that can cost a lot. So the ability to readapt the solution if the conditions change is very important. That's the full idea of the multi-criteria process there. So in summary, this is intended to help our planners to that conclusion that it says there, get from special studies to standard process. We're not naive. We don't We don't think that just by having this framework, everybody, all those sound will move to that. It's a process. It will take time, but it's a one step in that direction. And there's other things that we need to, based on feedback from members, from others, that could be included. Like, for example, resiliency metrics. We're not yet consider that. We may. Those are difficult to quantify, to understand. And the other aspect has to do more with the regulatory aspect, like how you capitalize that, right? It's the typical question, is a capital investment, DLR is cheap one, it's a capital, it's a OEM. So how do you consider those things? That's what I wanted to share with you today. Well, look forward to your questions during the panel.
Okay, right there. Hi, everybody. I hope you're all doing great. And thank you, Madeliene, for all the coordination, and James and the rest of the ESIC team for the show and having us here. So as this portion of the presentation, the focus is going to be more on key implementation challenges when it comes to transitioning from conventional type planning to grid enhancing technology enabled studies. Part of the challenges that we will share today are based on projects, collaborations we have had with different utilities in the past couple of years. Some may sound familiar to you, perfect, but I'm sure you do have also other observations, so please feel free to share those so we all learn from each other and consider this as a two-way communication. As for myself, Matt Mazhari, Director of Transmission Planning with Electric Power Engineers, been in transmission planning area for more than 10 years and in power system studies and advanced research for 15 years. So technology is always close to my heart on that sense. So speaking of grid enhancing technology adoption and the challenges on the way, this is actually highly normal to have challenges. So if we follow what Alberto mentioned, we probably will not have that many, but typically we do have these challenges. So that's why I thought it's good to start to describe why it is normal. So we have some initial stuff, and later on when we talk about those challenges, we can then connect the dots between the two sets and maybe root back. So natural inertia is the first piece. We all have that natural tendency not to easily accept a technology inside our routine type work. And transmission planning is also one of those. And it's good to mention this presentation is all from the transmission planning perspective. So if we talk about challenges, planning type challenges. The second piece is the checkbox compliance. This is at least the way I phrased it. So imagine you have technologies that are not that much mature, and at the same time, you have engineers like Matt who have that natural inertia. And then you want to support grid enhancing technology adoption via some compliance type programs, Order 2023, as an example. While your intention was to help, what you may end up with is a bright engineer in that utility will simply make a justification why that technology is not useful in that footprint. Checkbox, the compliance mark, done. They will stay focused on their large load study. So bringing things back from that bypass to the normal common sense is not that easy. The other piece is buzzword fatigue. So I mean, trust me, you talk to 10 transmission planners, to their managers, utility strategy engineers on grid enhancing technology. It is hard to believe that you don't hear one of these words, buzzword, overstated, exaggerated. So at least part of the community have a sort of perception, feeling about the technology. It's harder to get them back on track. So it's good that they have the concern, but it's good to know what their concerns are. Some of those ask that I don't know what this is. How do you measure success? And that's why the presentations that, as an example, Alberto had tried to cover some of these. So if we don't pay attention to how we are going to pave the way. So with that, in the rest of the presentation, we're going to focus on just these 5 challenges. Again, there may be more. I'm sure you'll be sharing some of your observations. Gap between technology understanding and practical application. Lack of clear solution methodology. Limited adoption of screening tool sets, model maturity, and interdepartmental coordination. So let's start with the first one. This is actually the one that directly impacts or related to our frontline workers, our transmission planners. So grid enhancing technology, and actually these type of technologies are not new to a lot of people, specifically a lot of fresh grads that we hired. Majority of those have advanced degrees, worked with these tool sets back in university. And at the same time, we do have a lot of lunch and learns, and we bring people to train them on what the technology is. But you ask them what the technology is, they explain in the best shape all the control, building blocks, mechanics. You ask them, can you please now try to solve this violation using get? They say, what? I know it, but not that much. But technically, theoretical awareness is there. There is just a small gap, that practical execution. So let me give you some examples, very correlated and relevant to what Alberto had on that good slide there. So we shared some violations, thermal, voltage, dynamic violations with different engineers, and we asked them to tell us which technology works. And they had an idea, very well trained on the technology concept itself. So these are some of the, as an example, mistakes that they made, which tells us that the gap is there. So a lot of those try to propose APFC for a very short line, less than half a mile. And there is no space for that device to be installed there. So why we are doing it? They knew the technology, but not this basic. So they had access to a bunch of dynamic voltage profile for different contingencies. We asked them which one of these can be solved by StatCom or SVC. A lot of those chosen a plot that was associated with a P5. P5 back in TPL category is for non-redundant protection. Redundancy in protection is very cheap, easy to add compared to adding a new device to your system. Radiality is another one. Actually, Alberto had that in his slide as well. So we asked them, before checking PSSC stuff, tell me which one of these violations you probably feel you need to investigate more. They started showing us some violations that were small, so APFC could fix, but the system were radial. That was the first time they ever understood why that radiality index is actually, as an example, in a toolset like TAR. Okay, I need to use it. So very similar stuff. They suggested transmission switching topology optimization highly close to a nuclear station, which we know is impossible. So I mean, there are gaps. So this is a challenge. How it can be resolved? I'll back to what Alberto had, that salient features, that is that we need to be able to translate the technology definitions to transmission planning. It would be some stuff fairly similar to what they need to know daily. And at the same time, they need to be equipped with some techno-economic stuff, more feasibility aspect of the work. Moving to the second challenge is actually what Alberto had technically on his presentation, is the lack of clear solution methodology. So we need to have something solid, like what Alberto mentioned. So imagine you have an engineer who knows the technology well, and then you also help them learn how to apply it in practice in transmission planning, but you don't give them that methodology that they need. We are performing state studies around from one area to another. We know it, we have the tool set, but to apply it in a new area, I still need you to tell me what is the procedure that I should follow. What are the assumptions? What are the power flow settings in your area? I know it, but I need to follow yours, because fairness is applying the same methodology for every project. So same here. They need to know it. So we cannot ask an engineer to test grid enhancing technology without giving them that step-by-step process. Second piece here is that that process that we are developing should exactly mimic the same conventional planning process. And that's another area of challenge that we observe around. If there is deviation, they will see a lot of differences in the results. The engineer will waste a lot of time just figuring out why the results are different. And another widely asked question is that, can I use the methodology developed for grid enhancing technology for another area? Maybe yes, but technically one size does not fit all. Areas that have generation durability concept, that have transmission service request studies, their modeling is different. We can't use it. Area like ERCOT that use connect and manage structure, again, we can't easily apply it to other areas. So as long as we have the exact same procedure, and not just in planning, also in protection, also on the design, yes, we can use, otherwise no. And last piece here is that, at least on the planning side, the main order that is associated with grid enhancing technology as of now is order 2023. This is around generation interconnection. So violation is a violation, regardless of the type of study you see. Large load, that violation is the same as TPL in terms of nature, generation interconnection study. So if we are going to have a procedure and we want people to follow, we technically need to have procedures for those as well, right? Third item, we will fall under limited adoption of screening toolsets. So imagine we have all the past two items covered. I need to perform a study, see the violations, evaluate the violations, develop a conventional solution first, and then test if grid enhancing technology can work. This is tail end of the process, timeline is crunch. How should I deliver? That's why I skip. So something that people can pay attention to specifically in cluster studies, you don't necessarily need to have everything covered in phase one. You can have your conventional solution and evaluate and tell them that maybe in phase two, for these facilities, I will test grid enhancing technology as well. So to be able to do that, we need to have a screening tool sets. Technologies that it's not just one, multiple of those. And they may work. And another challenge is that they will build a lot of sensitivities, so you need to study more. So complexity will technically push us to use toolsets. So as I said, lots of toolsets, but what we need from the toolset is to tell us first which violation for sure will not be solved by these technologies, and which one we have high chance to use, then we can study. So we also developed one for TVA as part of a project we had with them. But as I said, there are several tool sets out there in the market. Fourth item is model maturity and readiness challenges. So majority of the items we discussed are technically started for operation, not for planning. Vendors' mindset today is still on working with an APFC vendor, and I told them that, listen, I want a control technique on your device that will only let the device be active when loading of a line is above 100. Do you have that control scheme there? After a couple of weeks, they said yes. I said, do you have the model? No. Finally, they found a model that I don't know how to use it. I can use it actually inside PSC, but not inside other tool sets. So this is because they have everything for operation, but not for planning the way I want. And this actually connects us to the next piece, that those modeling challenges is one, but they should also be incorporated inside different tool sets that we have. Imagine I'm going to use APFC on generation durability study in an area like PJM. A RAS action inside. It just gets specific input, so I can't test it. So if someone in PJM told me that, yeah, I use APFC, I evaluate, I say, how did you do that? It's impossible now. So they need to work with those software vendors to ensure these models will be incorporated there. And you know what the issue is? I have a lot of large load studies, generation interconnection studies, timeline. I don't have time. I can't take the error. And I can't do a lot of sensitivity studies. So this piece is actually not for us, it's for vendors to get and resolve this challenge for us. And last challenge that we have seen around, which is again important to have a nice framework in a utility, is collaboration and coordination between different teams. Protection, operation, design must be involved, must have idea. They also need to develop their own procedures. If you are changing the network structure, and this is crazy different, they should also have seen this in their protection studies. If you are changing impedance of a line or dynamically changing it, do they have really a process to evaluate their protection scheme with dynamic impedance change? Majority of utilities don't. Operation the same. You need to get what they need. So in the planning stage, you bring that into your process. We talk about transmission switching, easy. You find a good transmission switching under an action. You talk to operation team. They say, good that you have it. When can I bring the system back to normal? So they have another question as well. So you need to now perform another study and define when the system should back. So if you don't know it, how are you going to incorporate that into your process? Design is another. Fairly simple. Imagine you suggest an advanced conductor, you talk to your design team, they say it's impossible to use this conductor. Say, why? This vendor is not approved. This conductor is not on my list. Adding a conductor to the approved list needs factory acceptance test, 2 years. So without having them early in, you will not get to know how to resolve the challenges. So as I said, these are the top 5 that we observed, but I'm sure that you do have a lot of other observations. So please feel free to share. Thank you. Back to Patrick.
Okay, let's see. Okay, seems like this is mine. First of all, thank you, Madeliene, for chairing this panel. Thank you to James and ESIG for the invitation. Also, thank you to all my previous speakers. It was pretty good. At least we still have some folks left in the room, which is great. And I know my job pretty well. I'm the last speaker. Do it fast. I'll do that. I'll also make sure that I don't hold you guys for your flights and stuff like that. So and also understand that yesterday was a reception. Went back at 10 o'clock. There's some friends over here, and so this was done at around midnight, late after midnight, right? So this was from that perspective. Having said all of that, so this is a utility perspective, right? I've heard from EPRI, I've heard from a consultant, I've heard from Grid Strategies. But this is what we deal with day in and day out, right? I'll stand in front of a regulator and I'll face the questions, right? So take it from that perspective. Okay, so these are disclaimers. Just want to make sure again that this is for informational and industry engagement purposes only, and we'll share some best practices as far as Xcel Energy is concerned. And I hope that if there are some utility friends in this room, they can take some insights from this presentation. So for the Xcel Energy footprint, many of you probably know here in 8 states, very diverse fleet of generation, load, and interconnection profiles, approximately 4 million electric and 2.5 million gas customers. We have OPCOs around MISO, SPP, and a non-RTO. So 1 and 2 in this map is MISO, 4 is SPP, and 3 is where we are today, which is Colorado, which is not within an RTO. From a planning context, the idea here is Xcel is trying to stand up a framework that will be used to do some get screening, right? It's also a requirement from the Colorado PUC. I've heard that it's a requirement from the Minnesota PUC. To some extent, it's also a requirement from some of the previous 4 rulings that was talked about. So this is sort of to make sure that you're all on the same page. So these are 3-4 corridors that deals with gets, right? So 1920, 881, and 2023. 881 is predominantly AIM-bit adjusted ratings. We have already made progress on that, on AIM-bit adjusted ratings for Xcel again. For 1920, the third point is most important. So it does talk about gets where it gets real complex for us. It does not talk about how to properly do cost allocation for gets, right? This is interregional planning 20 years down the line. So when I say 20 years down the line, some of the gets already gets ruled out to some extent. Cannot really forecast whether 20 years down the line. But anyways, and it also says that the minimum criteria includes everything greater than 200 kV, right? So again, that's what 1920 says. 2023 again is the Gen interconnection process. It asks or it recommends utilities to evaluate some of the GETS devices. By the way, this GETS the coinage came from some of these orders and the rulings from FERC and some of these recent things from DOE. So that's why we choose these 4 as GETS. What's going on here is a sort of a transmission problem, right? It's a timing mismatch. So you have loads which try to interconnect as fast as possible. You have a generation mix, and everybody wants to interconnect faster and faster. And building transmission takes time, right? Though you just need to do it, but it still takes time. So we see some of this gets as sort of a bridge between now and when we actually build transmission. So I want to highlight this point again, that some of these gets might help us to provide some relief during this window, but you do not, I again highlight this, we do not see this as a permanent substitute for building transmission. These are the 4 gets that we generally deal with. And again, this is based on the definition from FERC and DOE. So advanced conductors, this can be ACCC or any of the equivalents that you can think of. There can be, of course, DLR. You've heard about a lot from the previous presenters. It can be APFC, basically redirecting power flow across your lines, or it can be topology optimization, right? And I'll come to a slide where it'll show how we think about each of these techs. Okay, so this is the advanced conductor use case. So Xcel has a lot of experience in using advanced conductors. There are some cost savings, there's some ampacity increase, but everything depends on the fact that whether your existing structure can actually hold an advanced conductor. So that information is important, right? So from a planning perspective, when you go and talk with T-Line, they will tell us exactly what are the corridors where they can actually install an advanced conductor, where it works and where it does not. So that's what it is. There's some vendor range that we see. I'll not talk about much, but it's important that utilities do their own testing and come up with their own sort of matrices, other than the ones that are reported by vendors. And this also seems like this has been used throughout the globe a lot. Again, 125,000 miles installed throughout the globe. And there are more than 200 projects within North America. From a modeling perspective, it's probably the easiest of the lot, right? It's just it's a rating thing, right? So you can use it in PSSC, PSLF, ProMod. You talk it, you can do it, right? So this is the easiest one. Some of the key risks that we think about is, again, whether it can be installed, whether your structures can actually hold an advanced conductor, and then if your terminal equipment do have the capacity or not. It's not a huge deal. I mean, if not, you can always upgrade those terminal substation equipments, but that's something to think about. So Xcel first deployed its first advanced conductor back in 2005, and from there onwards, tens of miles, I think close to 100 miles at this point, has been deployed across Xcel's territory, mostly in Colorado, New Mexico, and Texas. And there are projects in the pipeline that will be using advanced conductors. So of course, we have lots of experience in dealing with advanced conductors. And as I said, the planning tool compatibility here is very easy. I mean, you can put the ratings in any tool that you use and it should work just fine. There is a design standards opportunity. So we have formed design standards for the normal conductors, but currently we are trying to stand up a design standard that will be used across the opcos for advanced conductors as well. And I think I mentioned this before, the structural validation is important. So we talk a lot with our T-line teams. They tell us exactly whether this can be done or it cannot be. So this is not super important. So there is a cost premium to use advanced conductor, what we have seen versus, let's say, traditionally CSR. And so that's a risk category that we deal with. But again, we have to consider this as a long-term investment and how this plays sort of over time. So next is DLR. Again, you have heard about DLR a lot from my previous panelists right here. The way we think about it is, so there is a need, and that should be a justifiable need coming from the studies and stuff like that. And then, of course, you have the physics, which is, IEEE 738 and so on and so forth. And then you have, data from sensors or maybe sensorless even, that's fine. And then what you do in planning is you either run a 8760. So Xcel has an internal tool that can actually run 8760, or you take some probabilistic ratings, right? You can say, hey, what's my 90th percentile ambient ratings, right? So you can use some of that in your studies. In ops, and I have mentioned this to multiple vendors, that make sure that you know that you can integrate your solution with EMS. Unless that happens, it's a no-brainer that will not use it, right? So there are not many EMSs in the world. There are not many EMSs vendors in the world. You all know the names. So make sure that your whatever you're developing is at some point can be integrated with our EMS that you all use. Planning study, again, as long as you can use some of those capped DLR ratings, you can use them for any study that you want. Or we can run 8760 time series analysis. That's okay as well. And ideally, that should actually happen. If you cannot run time series analysis, then you probably have to do some sort of a capped rating. And same for economic planning as well. And when you do this, the idea is also we should document the risks. Stage, some data quality issues, and what's your overall life cycle maintenance plan. So some of these gets sorted through the warranty that we get over a period of time and so on and so forth. So that's the idea. If it's a sensor-based DLR. Okay, so the next is APFC. Again, just redistribution of the flows, right? So you have a circuit which is overloaded. You have you have a few others which are not. So can you redistribute the flows between these circuits? So that's the overall idea. From a planning perspective, once again, I mean, size it properly. That's important, and there is basically not many vendors who supplies APFC. We all know the names again. And the problem that we deal with is there is no sort of off-the-shelf APFC device. You have to basically size and spec it for every single application, right? And from a study perspective, modeling APFC devices in steady state is easy. For dynamics, it's slightly difficult. You can still do it in PCC and some other tools that we use. But I have been told that the vendor is working with the standard software tools, and the next version that's coming out, it will actually have a dynamic module dedicated to APFC as well. So that's where it is. I think this was mentioned by my previous speakers as well, that substation space requirements is key. We had a use case where APFC would have been a perfect fit, but it was figured out after consulting with the substation team that we just don't have the space, right? So that's important. If there are multiple APFCs in the future, then control architecture and how they're fighting with each other needs to be looked at. EMS model currently for APFC. Again, I know a EMS vendor that's working towards it, but currently it's still in development. So this is the APFC landscape for 2026. We talked with multiple utilities, both in US and one in Australia, how they're using APFC, and they have all told us that even if they have deployed APFC, it's in static position, right? They're not using APFC to quote unquote dynamically control the megawatt flow. And this is due to the operators not having trust in having a device play by itself. So that's the idea. And if at all we finally decide to put APFC somewhere, I think this is where we'll start with as well. I mean, it will take some time for our ops folks to even get comfortable with the device playing on by itself. As I said, I mean, we did a study on APFC. There was a nice use case, but the problem was there was a substation constraint, and then what happened was the redirection of power flow also didn't quite work the way we would have loved it to be. Some of the use case, again, unscheduled flow mitigation. Some ISOs, RTOs, I know are trying to do some of that. Parallel path loading enforcement, and if there is a possibility of some interim congestion, I think that's a good use case as well. So this is how Xcel tries to think about APFC. So again, identify the constraint identification. Has there been any alternative analysis that has been done, right? So pair APFC with a PST, right, with a phase shifting transformer or PARS, what you used to call it, and see how the comparison works. And then there'll be a governance gate, due to capital planning and project approval through Xcel standard process. And then hopefully there'll be a pilot with a vendor. And at some point when it's deployed, it will be static, and the operators will get to control that. So it will not be a dynamic device for us. And the CMS integration and stuff like that needs definitely to be looked at. Topology optimization. This is something that I know, not many, but maybe at least two ISOs have good experience with. I see Mariana in this room. She has done a lot of work with SPP due to outage coordination with topology optimization. And this is going on for years. This is nothing new, actually. From our perspective, the main problem we deal with is we don't have a good node breaker model, right? So all our models are generally bus branch. It's not like we cannot create one, but we don't have it at this point. So that's what we deal with. So unless we have a good node breaker model, you cannot really do switching actions. And then again, this is how we think about it, integrate real-time data, streamline and automate the studies. So the idea here is, first track the post-contingency only cases through some expedited reviews. And if something has worked in the past, note it down, maybe it will work in the future as well. And we should always consider the voltage constraint topologies as well. I mean, we've seen some of these things happening when we were testing some of these things out. And again, improve transparency and build a library of proven actions that can be used in planning, right? So I'll not go into too much detail. I don't think I have much time left. So this is, so I know I talked about SPP. I think they have already implemented to some extent the TTO. I think MISO had a case study about congestion. And then, so two of our opcos, as I said, one is with MISO, the other is with SPP. They can definitely take some of these RTO outputs and use some of that in planning. But again, I mean, for us in PSCo, we're still looking for a good node breaker model. We can grab some of that from SPP, but unless we sort of institutionalize a node breaker model inside planning, it's still difficult to do topology optimization to some extent. So this are the modeling and study requirements across all the GETS families, right? So this is advanced conduct, as I said, it's pretty easy to model. All the current tools can model something like this. For DLR, AAR, we're already in AAR, so institutional process to do AAR. For DLR, we're probably looking at either running 8760 or doing some probabilistic analysis. For APFC, again, if it's series controlled, it's pretty easy to model in steady state. For dynamics, there's workaround to model that now, and again, I think in the next version of some of the softwares, we'll get a good model. For TTO, I think the problem is, again, from a planning perspective, we do need a good node breaker model. We should consider all the scenarios that might happen. And if something has worked in the past, we should have those library of actions that has been previously taken. And this is sort of the planning to operations process. You have forecasted needs, you have run your alternative analysis, you have done your engineering validation. Is ops ready with this, and how is the performance management going to happen? And also, there are multiple governance gates that we deal with at Xcel before we actually say that, okay, this is the tech that you can go ahead and put in the field. Okay, this is my final slide. So there are some benefits that we do want to quantify with GETS, and there are some risks, right? So at the end of the day, the benefits needs to override the risks, and only when that happens, we will say that a GETS is one of the GETS candidates is a good use case. But until that happens, it's not. And again, I'd like to say that it's not a substitute for building transmission. It'll still build transmission. That's what is needed. But as a bridge, sure, you can use some of these technologies depending on the use case. I think that's what I had today, and thank you.
Is this working? Great. Thank you to all of the presenters. I'll invite any audience members, if you have questions, to please step up to the mic. I see